Hello, my name is Zeeshan Shariff, and I'm a senior at West Windsor Plainsboro High School North. Today, I will be presenting my project analyzing the 2011 Japan Tohoku earthquake, specifically the strain distribution and displacement. Firstly, some background. Japan is one of the most tectonically active countries in the world, accounting for 10% of global earthquakes. This is because it sits on the border of 4 tectonic plates, as you can see on the map of your left. The Eurasian plate, the North American plate, the Pacific plate, and the Philippine Sea plate. Earthquakes are caused by the interactions between these tectonic plates. Over time, stress can build up between plates and suddenly be released in the tremors we know as earthquakes. Thus, because Japan lies on or near the border of these 4 plates, it experiences a lot of earthquakes. Speaking from personal experience, due to my upbringing in Japan, earthquakes are a part of daily life. Students frequently practice earthquakes and flooding drills, and small tremors occur regularly. Numerically speaking, on average, Japan experiences 2 to 3 earthquakes a day. Of course, not all of these are noticeable or major ones. However, a particularly significant earthquake was the March 11, 2011 Tohoku Oki earthquake, which was of magnitude 9.1 and thus stands as the most powerful earthquake ever recorded in Japan. For context, in New Jersey last year, we experienced an earthquake of magnitude 4.8, which caused noticeable shaking in buildings for about a couple minutes. But because the earthquake scale is logarithmic, the Japan earthquake was about 20,000 times more powerful than the New Jersey one. As you can see on the map on the right, the epicenter of the earthquake was off the coast of Sendai. This catastrophic event caused widespread destruction, including a massive tsunami wave and the meltdown of the Fukushima Daiichi nuclear plant. In addition, it caused the extensive displacement of Earth's surface, the topic of my study. Understanding the impacts of such an earthquake would assist in both scientific and practical purposes, including in fields like earthquake hazard assessment, disaster preparedness, and infrastructure planning. The study of displacement patterns would also allow researchers to gain insight into the underlying tectonic processes that in the region and to better understand future seismic activity, especially their location. Hence, the primary objective of the study is to develop a displacement model for the Tohoku earthquake using GPS data. GPS data is incredibly effective at tracking ground movement because these stations can detect changes as small as a few millimeters. Unlike seismometers, which detect wave motion, GPS gives us an actual position shift. In other words, it can show us where the land physically ended up after the earthquake, which should give us a useful visual image to understand the impacts of the earthquake. This model will be used to analyze the spatial effects of the earthquake's surface displacement. The findings of the study will provide valuable data for researchers in the field of geology, seismology, and civil engineering, contributing to global knowledge on earthquake-induced geological phenomena. Similar GPS displacement models have been used in other major earthquakes, for example, in the 2010 Chile earthquake and the 2004 Indian Ocean tsunami event. In each case, GPS data helped researchers understand the earthquake better, including its magnitude and impacts. So while my study focuses on Japan, the methodology can be applied to other earthquake-prone regions. The source for the data came from the University of Nevada's Reno's Geodetic Laboratory database. The data included daily position recordings from over 900 GPS stations across Japan, captured in a 10v3 file format, with timestamps dating back to 2009. A screenshot of the data from station J005 can be seen in front of you. The highlighted boxes are what is the data used in the analysis. As you can see on the left, we have the date of each data. So in this case, January 1st, 2009, and stretching onwards until modern day. And then on the right, the positional data. So east-west position, noted just here as east, and north-south position, noted here as just north. Using R, the data was scraped from the database to calculate displacement between March 10th, 2011, a day before the earthquake, and March 12th, 2011, a day after the earthquake, for every Japanese GPS station possible. As I will discuss later, this process could not be done for certain stations. Let's take a quick example. Let's say we have some certain station, which on March 10th recorded a position of A meters north and B meters east. Then, on March 12th, it recorded a position of C meters north and D meters east. We can calculate the displacement of this station using a simple distance formula. So the square root of A minus C whole squared, where A minus C represents the north-south displacement, plus B minus D whole squared, where B minus D represents the east-west displacement. In regards to the angle of the displacement, you can use the arctangent function to get the angle in coordinate form. So in this case, arctan of A minus C divided by B minus D, the north-south displacement divided by the east-west displacement. Then we need to convert it into bearings for the software that we use. A common challenge with large data projects like this is dealing with the messiness that often lies in the datasets. While this GPS data was well maintained, an issue I faced during this process of calculation was properly converting the data from the column form you see here into the numerical form used in the calculations we just discussed. This is because, as you can see on the right, the data is split into two different columns. A whole number column, so east 0, or E0 I mean, where the data is just 3,963, and then a decimal form, which is east meters. So this is 0.16, 0.15, etc. The actual position is the combination of these two data points, so 3,963 combined with the decimal of 0.16, so 3,963.16. Or in the case of north-south, around 4,800,000, 0.936. However, the whole number column was not updated properly. So for example, imagine if instead of 0.9, it said 1.2 on the right. 1.2 is not a decimal. What should have happened is that the 1 should be transposed onto the whole number column, updating it by 1, while keeping the decimal a decimal. However, this did not occur, and thus, as a result, my code ran into a bug where it interpreted the 1.2 as a 0.2, significantly reducing the apparent displacement caused by the earthquake. This was eventually fixed by accounting for this overflow. Once we did these calculations, we ran it through every single GPS station possible, exported it to a list, and then brought that list to ArcGIS, a geospatial analysis and mapping tool. In addition, we also took the latitude and longitude posted for each station and used them to plot each GPS station on a map of Japan, and combined it with this displacement data. The size and angle of each arrow that we created varied according to the magnitude and direction of displacement. The resulting displacement model was then analyzed using a qualitative approach. The picture on the slide right now is the model that was created, a screenshot of the model that was created as a result of the calculations. Each blue dot represents a GPS station, while the arrow's direction and size represents the magnitude and direction of the displacement, as per the key provided. In the bottom right is a tectonic plate of Japan, just to give some context on the area that we're analyzing, as well as the tectonic context. In the northern parts of the figure, the displacement shifts in a southeastward direction, contrasting with the northeastward shift observed in central northern region. This differential movement points to compressive forces acting within these areas. Most notably, some areas experience displacement of up to 2 meters, around 6 feet, which underscores the immense scale and intensity of the earthquake. Now, as you can see on the the west, some of the GPS stations appear to show no movement. However, these regions experience only minimal movements compared to the more heavily affected areas, and thus, although arrows are being displayed, their size is too small to see with this picture, and the scale used. This could be due to local geological conditions or the distance from the epicenter. On the other end of the spectrum, near Sendai, there's a large gap of GPS stations. This isn't because there are no GPS stations, but rather the fact that it was so close to the epicenter of the earthquake that the violent tremors caused data to go missing from March 11th to around either a week afterwards or a month afterwards, depending on the data. However, some of the data in some of the stations implied that this area had a displacement of up to 3 meters, or close to 10 feet. The observed shifts align with the expected geophysical events of a large magnitude earthquake, such as the Tohoku one. The ripple effect of displacement, where the displacement progressively gets weaker the further away you go from Sendai, suggests the outward propagation of seismic energy, with the most substantial displacements occurring closer to the epicenter. The shear movements along the western and eastern coasts further indicate tectonic stress in those areas, likely due to the complex interactions between tectonic plates. Overall, the Tohoku earthquake caused displacements in varying directions across central Japan, leading to compression and shear forces. These forces likely contributed to the buildup of stress and strain in certain regions of the country. Further research is needed to determine the underlying causes of these displacement patterns. For example, preliminary investigations suggest that the rock composition of different sections of Japan, seen on the right, may influence both the magnitude and direction of the displacement. Additionally, the presence of minor faults across the country could play a role in these movements. Further studies, including analysis of aftershocks and subsequent seismic events, could enhance this model's ability to predict stress buildup. Such analysis may help identify potential areas of future seismic activity, offering valuable insight for earthquake hazard assessment and disaster preparedness. So, to recap, we used GPS positional data from over 900 stations throughout Japan, processed them in R to obtain the displacement magnitude and direction, visualized it using a software called ArcGIS, and discovered regionally varying displacement of up to 2 to 3 meters following the March 11, 2011 earthquake. All of this contributes to a better understanding of a seismic behavior during megathrust events like the one we analyzed. These are my references. Thank you so much for listening to my presentation.